What is up, young chemists? Mr. Rosen here. Today we're going to take a little bit of time to talk about the specific heat capacity calculations from our most recent lesson. In this lesson, we'll do not only specific heat calculations, but also phase change calculations and multi-step calculations. So first, we'll just talk a little bit about what specific heat capacity is. So the specific heat capacity is the amount of energy that's required to raise the temperature of 1 gram of a substance by 1 degree Celsius. So if you had a gram of water, the amount of energy it would take to raise its temperature by 1 degree would be called its specific heat capacity, and that is 1 calorie. Okay, a calorie by definition is the amount of energy it takes to raise 1 gram of water by 1 degree Celsius. A calorie, with the lowercase c, is equal to 4.184 joules. Okay, joule is another unit of energy. This is a last name after James Prescott Joule. It's pronounced like you have a jewel on like a piece of jewelry. So the equation we're going to be using to do specific heat capacity calculations is written here, where we have Q equals ms delta T. Q is your energy value, which will either be in joules or calories. M is your mass, which is usually in grams. S is the specific heat capacity, and the units for that are either in joules per gram degree Celsius or calories per gram degree Celsius. And then you have delta T, which is change in temperature, and it's really important, that's why it's in bold. Delta T is always final temperature minus initial temperature. Okay, if you do this, then sometimes you get a positive number, sometimes you get a negative number. It's really important because when you do the calculation, that will give you either a positive or a negative value for Q, and that tells you if the process is exothermic, meaning energy is going to be released to the surroundings, or if it's endothermic, meaning energy is absorbed from these surroundings. So let's do an example problem. So the first problem says, how much heat in joules is required to warm 82 gram sample of water from 62 degrees to 88 degrees? Okay, remember, the specific heat capacity of water is 4.184 joules per gram degree Celsius. So first we're going to identify each variable. All right, so Q is what we're solving for. Okay, that's what we don't know. M is the mass of the water, which is 82.0 grams. S is the specific heat capacity of water, 4.184 joules per gram degree Celsius. And then delta T is our change in temperature. Now remember, change in temperature is final minus initial. So our delta T is going to equal 88 minus 62. So our delta T is going to equal 26 degrees Celsius. 26 degrees Celsius. So now that we know what they all are, we're going to be plugging them into our equation, which is Q equals ms delta T. So Q equals M, 82.0 grams, S, 4.184 joules per gram degree Celsius, and then delta T is 26.0 degrees Celsius. Now, these are all positive numbers, so our Q is going to come out to be a positive number. And if we plug these into our calculator here, it's going to be 82 times 4.184 times 26. Now we get this number, which will round to 3 significant figures, would just be 8,920 with no decimal point. This is joules, okay? Grams will cancel and Celsius will cancel. And we're left with Q in joules, which here is our final answer, right? Q is 8,920 joules. So I just rewrite that. Notice Q is a positive value. So if Q is positive, that means that this is an endothermic process. So that means that this amount of joules is required in order to raise the temperature. And that makes sense because you have water at one temperature and you want it to go to a higher temperature. That energy needs to be supplied to the system from the surroundings. And this is the number of joules that are needed. Okay, now at the bottom there's a little note and it says that some problems are having you solve for Q, which is what we just did, but there are other problems where you have to solve for any of the other variables. So you'll always have 3 of the 4, and you'll be solving for the unknown. And we'll do some practice with those right now. So some will solve for Q, some will be solving for a different variable. So let's try some more of those out. These are specific heat calculations, okay, specific heat calculations. So number 1, zoom out a little bit. It says, determine the energy required, so that's Q, to raise the temperature of, so here is the number of grams, that's our mass, aluminum from, okay, this is going to be our delta T, and then it tells you the specific heat capacity of aluminum is 0.9 joules per gram degree Celsius, so this is S. So Q equals ms delta T, right? Q equals ms delta T. So we're just going to start plugging things in here. Q is going to equal M, which is 59.2 grams. S is the specific heat capacity, which is 0.9 joules per gram per degree Celsius. And then our delta T. Now delta T is final minus initial, so delta T is going to equal 78 degrees Celsius minus 35.8 degrees Celsius. So our delta T, we'll just put that in there, 78 minus 35.8, 42.2 is our delta T. So now we're going to multiply these numbers. Okay, 42.2 times 0.9 times 59.2, and Q equals, okay, rounding to 3 sig figs, it's 2,250. This is joules. Now, this is a positive value, and that makes sense because this says energy is required, which means the system needs to gain that energy from the surroundings because we're warming it from 35 up to 78. So that's just another problem solving for Q. Now we're going to do a problem that's solving for a different variable. So number 2 says if it takes 60.25 joules. Now you notice this is joules. Joules is our unit for Q. So that is our Q. All right, now it's a piece of gold which has a mass of, this is our mass, about 18 grams. And then we have a temperature change. And the question is asking what is the specific heat capacity? So Q is 60.25 joules, and Q equals M, which is 18.69 grams, S, which is what we're solving for, and delta T. Now delta T is final minus initial, so 35 minus 10 is 25. That is our temperature change. So Q equals M S delta T. We don't know S. We need to solve for S. So if you solve for S, you're going to get S all by itself on one side of the equal sign, so we're going to divide by 18.69 grams times 25 degrees Celsius. Those will cancel, and just leave you with S on one side. Now if you notice, you're going to end up taking joules. Whatever we do to one side, we do to the other. We're taking joules and we're dividing it by 18.69 grams times 25 degrees Celsius. So in terms of our units, joules is getting divided by grams times degrees Celsius. So S, our specific heat capacity, is joules per gram degree Celsius. Right? Now when we do this, let's plug them in here. It's going to be 60.25 divided by the product of 18.69 times 25, close parentheses, and round that to 3 sig figs is 0.129. So 0.129. That is the specific heat capacity of gold. 0.129 joules per gram per degree Celsius. Now, number 3 is a problem where you are actually, again, given joules. So joules is given, so that's your Q. Heat's applied to a sample of copper, heating it from 25 to 57, so that's your delta T. What is the mass of the sample of copper? So we don't know what the mass is. Now it tells you the specific heat capacity of copper is, so this is our S. So again, we have 3 of the 4 variables. Q equals, sorry for the bell, one sec. Q equals ms delta T, so 2887 joules equals M, which we don't know, S, which is our specific heat capacity, which is given, and delta T. Now our delta T is going to be our final, which is 57, minus our initial, which is 25, and that's going to be our delta T, which is 32 degrees Celsius. So just like we did in the problem above, we have to solve for M. So we're going to divide by the other stuff on that side. So I'm dividing by S times delta T. If we do this, it will cancel out on one side. Right? So, and just leave you with M. So these cancel, this cancels. Whatever we do to one side, we do to the other. So our joules gets divided by our specific heat capacity. And this is times our specific heat capacity is getting multiplied by our temperature change, which is 32. Now if we do this, degrees Celsius is going to cancel and joules is going to cancel, and the only unit you'll be left with is grams, which is good because that's our unit for mass. So this is the number actually that's going to go on bottom when you multiply these two, and then you're going to take 2,887 and divide it by that number, and we get about 234 grams. That's the mass of the piece of copper. So the piece of copper is 234 grams. And you could always double check your answer if you wanted to plug that back in there. If you took 234, right, like if I could just do this and I'd say 234 times 0.385 times 32, and it should give us a number that's pretty close to what we started with here. It's pretty close. I think I just did some rounding, obviously, at the end there. But if you don't round, it will be very, very close to that. Okay, now those are all problems where there's a change in temperature, right? A change in temperature, there is always a delta T. So there is also a style of problem where you are solving for a phase change. Okay, so these are phase change calculation problems. And during a phase change, there's not a temperature change. So during a phase change, all you have to do is know the mass of the substance and what the heat of phase change is. So, for example, there's a heat of fusion or a heat of vaporization. That's unique to each substance. But the heat of fusion or heat of vaporization is usually in joules per gram. There are also molar heat of fusion or molar heat of vaporization. That's the amount of energy to turn 1 mole from a solid to a liquid, or the amount of energy required to turn 1 mole of a liquid into a gas. But if it's not molar heat of fusion or molar heat of vaporization, then it's probably in a per gram kind of thing. So Q is the mass times the heat of the phase change. I think the easiest way is just to do some examples here. So this says, how much heat in joules is required to turn 35 grams of water at 100 degrees from liquid to gas? So it's already at 100 degrees, so we're not going to have any temperature change. We have 35 grams, so that's our mass, and we are turning it from a liquid to a gas, so we have a phase change. Now it tells you the heat of vaporization is 2,260 joules per gram, meaning to turn 1 gram of water at 100 degrees Celsius from a liquid to a gas requires 2,260 joules. We don't have 1 gram, we have 35 grams. So we're going to be multiplying those two numbers. You can see mass times heat of phase change will give you Q. So Q is our unknown, mass is 35 grams, and I'm going to write H vape, so that's just heat of vaporization, equals 2260 joules per gram. So this is joules per gram, and we have 35 grams. So to do the math on this, it's pretty easy. Q equals 35 grams times 2,260 joules per gram. Okay, grams will cancel out, and you'll end up with your answer Q, which will be in joules. And if we plug these in our calculator, 35 times 2,260, we get this number. We're going to round that to 3 sig figs, so we'll just say 79100 joules. So note this is a positive number. That means that that's how many joules are required to turn 35 grams of water, liquid water, at 100 degrees into vapor. So at the bottom of the page it mentions you're not expected to memorize heat of phase change values, but something that's interesting to know, heat of fusion is 333 joules per gram approximately. Crystallization is the opposite of fusion. So fusion is a solid going to a liquid. Crystallization is a liquid going to a solid. So if this is the amount of energy, notice it's positive, this is the amount of energy required to melt a gram of ice, that same amount of energy is going to be released when 1 gram of liquid water turns to ice. So heat of crystallization and heat of fusion are the same value. One is required in order to melt, one is released. Okay, same thing applies for vaporization, right? We just saw heat of vaporization is 2,260 joules per gram, meaning that's how many joules are required to turn 1 gram of 1 gram of liquid water into gas. Condensation is going from a gas to a liquid. It's that same value, 2260 joules per gram, but negative because that's the amount of joules that will be released when 1 gram of water vapor condenses to a liquid. So they're the same numbers, the signs are just flipped. That's a useful concept. So we'll solve a couple of these practice problems, and then we're going to do one that combines them all. Okay, so question number 1 says, how many joules does it take to melt 75 grams of ice at 0 degrees Celsius. So it's already at 0, there's no temperature change. The heat of fusion is 333 joules per gram. So Q equals M, which is 75 grams, times our heat of fusion, which is 333 joules per gram. Gram will cancel out, and you'll be left with your number of joules. So we are just simply going to take 75 times 333, and we get this number, which will round to 3 sig figs, which will be, well, on the calculator, it's 24975 joules, which the only way to write that in scientific notation in 3 sig figs is to write 2.50 times 10 to the 4th joules. So that's how we're rounding to 3 sig figs. The next question says, how many calories, so it's not joules this time, it's calories, are given off when 77 grams of water vapor condense to form liquid water? Okay, now, it tells you the heat of vaporization, but again, vaporization is going from a liquid to a gas. But here we're going from a gas to a liquid. So we're actually not using heat of vaporization, we're going to use heat of condensation, which is going to equal minus 539.4 calories per gram. So Q equals 77.0 grams times minus 539.4 calories per gram. If we do this, we get Q, and Q should come out to be a negative number because this is going to be an exothermic process, right? Going from a liquid to a gas, vaporizing, requires energy. Going from a gas to a liquid, condensation, releases energy. So we're going to take 77 times minus 539.4. And what you get is this number, which will round to 3 sig figs, which would be about 42, well, actually, it's minus 41500 joules. If we go to 3 sig figs. And because it's negative, that tells you that that is the amount of energy that's going to be released or given off when that amount of water vapor condenses. Now we're going to do one final style of problem. Okay, so far today we've done Q equals ms delta T, so that's when you have a temperature change. And then we did some Q equals mass times heat of phase change, where it's during a phase change. It's not a temperature change. Okay, so we've done those two separately. Now question number 1 requires you to bring multiple skills together here. So question number 1 says, how many joules are needed to heat 225 grams of water from 65 degrees Celsius to 125 degrees Celsius? And then there's a bunch of information given. Now you might be tempted to just do a regular Q equals ms delta T problem, right? But if you look at these temperatures, 65 degrees is liquid water. 125 degrees is going to be water vapor, right? We're assuming just normal atmospheric, 1 atmosphere pressure conditions. So this is actually 2 different phases of matter. So in terms of like if we were drawing a heating cooling curve, right? If we were drawing a heating cooling curve, it goes up and then flat and then up and then flat and then up, right? This is your temp and this is when you're adding energy. So this is just a generic one. This section down here is the solid section, this is the liquid section, and this is the gas section. So in this calculation, this problem, we are taking liquid water from 65 degrees Celsius, which right here we'll say is 65 degrees Celsius, okay, right here. And it's going up to 125, sorry, that's 125 degrees Celsius. So we actually have a temperature change. We're going to say that this is 100 degrees Celsius, right? That's the boiling point. So this phase change is boiling. So in this problem, we have to go from water at 65 up to water at 100. We then have a phase change, and then we go from water at 100 up to, we have gas at 100 up to gas at 125. So this is actually 3 different calculations. There's going to be Q1, there's going to be Q2, and there's going to be Q3. Q1 is warming the water, Q2 is the phase change, and Q3 is warming the vapor. So we have to do each of those differently. Okay, so Q1 is going to equal our mass, which is 225 grams. Our specific heat capacity, which it's liquid water at this phase, so we say 4.184 joules per gram per degree Celsius. And then our temperature change here, it's from 65 to 100 because that's where the phase change is. This is 100. So delta T here is going to be 100 minus 65. 100 minus 65 is 35 degrees Celsius. Okay, so Q number 1 equals, we're going to plug these all in, 225 times 4.184 times 35. Okay, so 32949 joules. Okay, I'm just writing these down. Now, that is how much energy is required to warm the liquid water up to 100 degrees Celsius. You now have a phase change. So Q2 is going to be your mass, which is 225 grams, times the heat of phase change. And going from a liquid to a gas is called vaporization. So heat of vaporization is 2,260 joules per gram. So if we take 225 times 2,260, we get 508,500 joules. So that's the amount of energy required to boil all of the liquid water. So Q1 was going from 65 degrees up to the boiling point. That was at Q equals ms delta T because we had a temperature change. Then Q2 is the phase change. It's just mass times heat of phase change. And now we have 100 grams of vapor. Sorry, we have 225 grams of vapor at 100 degrees Celsius, and we need to warm it up to 125 Celsius. So this is our third calculation. This is Q3. It's Q equals ms delta T. 225 grams. Now the specific heat capacity is of water vapor because we're now in the gas phase. So that is 2 joules per gram degree Celsius. And our temperature change is final minus initial, so 125 minus 100, which is 25. If we do this, we get Q3, which is 225 times 2 times 25, 11250, and that is joules. So we just calculated Q1 is warming the liquid water up to 100, Q2 is boiling the water, and then Q3 is warming the vapor up to 125. You have to add these all together, okay? You have to add them all together, and if you do, you get the total Q, okay? I'm adding them all up, right? Add them all up. So I'm just going to add these together, plus 508500 plus 32949, and I'll just say Q. I'll write total down here. 552,699 joules. So that's going to be the total number of joules that are required to warm the liquid water up to the boiling point, boil the water, and then warm the vapor up to 125. These problems are about as complicated as they get. You have to do 3 different Q problems: a temperature change, a phase change, and a temperature change, and then you add them all together. All right? Hopefully you have found this helpful. We did specific heat calculations with temperature changes, with phase changes, and then a problem where we brought them all together. All right? Keep studying. Work, work, work. See you back in class.